Hello everyone, I want to thank you all for stopping in today. We have a wonderful special guest coming to talk to us all about building virtual and augmented reality experiences, given that we've been doing our series on Seashell and how we want to take our user interfaces and scale them across devices and form factors. Thought it would be really awesome to hear what the thinking is just down the hall in HoloLens land. So, Michael, welcome. Thank you for joining us.
Thank you.
Go ahead, take it away.
Okay. So the talk I'm going to give today is focused on basically describing how the technology behind HoloLens works that's different from other platforms, and specifically with the focus on how application developers can exploit that difference. So in other words, it's not meant to be a talk aimed at having you be able to create such a platform, but there will be enough information about how the platform works behind the covers in order for you to understand what its strengths are and what its weaknesses are and how to exploit them and work around them. So often I've given this talk to game developers or other application developers, and I feel like it's probably an appropriate talk to give in this audience as well because it's a similar kind of style of audience. A lot of the same kind of concerns come up. So with that context, I'll tell you a little bit about myself. So I used to be a game developer, and so I, in some sense, consider myself to be a game developer on loan to the platform team, although I've been on loan for 4 years and with no end in sight. I used to make Madden. I was the architect of the football sports business unit at EA Sports, and that group included Madden. But that's probably the one that, if you've heard of anything, in a video game-wise, you probably heard of Madden, if you've heard of anything I've worked on. I also worked on a visual effects system there, and that's used in all the EA Sports games. And I also do visualization, or I also do fluid simulation, which involves a lot of three-dimensional visualization. I also used to teach at UCF in a graduate program for how to build video games, and now, of course, I work at Microsoft. So first I want to tell you some basics about AR. A lot of this stuff might be familiar to you already, but I want to review it partly so that we're all on the same page, and partly because there are certain assumptions or maybe categorizations that you might be making that I'd like to explicate and maybe expand upon. So I'm going to describe what is meant by augmented reality, or at least in part what most people think of as augmented reality, and then go maybe a step beyond that. So here's a video which shows a holographic or virtual character, in this sort of real scene. And this is taken from a train that is driving past this scene, and this is on a phone. And so the video is jittery. The actual, I don't know what, the video playback is jittery, but this jitter that you're seeing here is not an artifact of the AR system. It's an artifact of the media player on this situation. Like, it doesn't always do this jittering thing. So I just want you to be clear that the jitter is not part of AR. So one of the thing, this, it could be because I'm trying to pass this through to Skype as well, who knows. This video is made by a colleague of ours named George Klein. This was part of his PhD thesis work, and he works on the HoloLens system. So I want to take a single frame of this and take it apart to show you what aspects of this are crucial for augmented reality. One of them is the fact that this character seems world-locked. In that video that I was just showing you, even though the camera was moving around, the character was moving around in screen space in such a way that it makes it consistent with it being an actual object in the real scene. So that's what I mean by when I say world-locked, is basically it looks like it's stuck to the world. Another aspect is that he is occluding the stuff behind him. And later on, I'll be talking about the sort of converse of that, is that the other objects can occlude real objects. That's an important aspect. And then a third aspect that you don't see in this video clip very clearly, but I'll cover it some more later, is that he seems to have a sort of two-way physical interaction with the world, meaning he's not falling through the world, he's not interpenetrating real-world objects and that sort of thing. So these are the basics of AR, meaning that you've taken reality and you've augmented it with some sort of thing that feels like it belongs there. And world locking is probably the most crucial part of that, but the other aspects sell you on that illusion. Another important aspect in the sort of state of the art right now are the kinds of rendering technologies. And so HoloLens uses a kind of rendering that I'll call additive rendering, which it means that we can add light to the scene. We can't take it away. And in a lot of Hollywood depictions of holograms or this kind of technology, it's an additive rendering. So here's a frame from Iron Man, and here who knows what kind of projector is creating this. It's just fiction. It doesn't really matter. But the point is that it's adding light, and it's doing so in a way where the amount of light being added is just barely enough so that you can see this at all, and so you can see right through it. Even though the background is dark, this thing looks kind of diaphanous and insubstantial. It's just there to give you kind of an impression. This is a typical Hollywood depiction. It isn't actually particularly realistic. And I think when people hear that we're making holograms, this is what they're thinking it will look like. When you put on the device, what you realize is that adding light has a lot more substance than just this. It doesn't actually seem like it's translucent as long as you're using bright colors. Now, if you render black or dark colors, it does seem more see-through, or if the background is very, very bright, then it does seem kind of translucent. But in this room, for example, which is fairly dimly lit, if you put on a HoloLens and we turn the brightness up to even a moderate level, you would not have the impression that it was translucent. It would look quite solid. But that's partly out of the choice of rendering bright colors. So one of the key takeaways is if you're using an additive display, then you don't want to render black if you want the object to feel substantive. In contrast to this is another kind of rendering, which I'll call composite rendering, and this is also a kind of Iron Man thing. And again, the video playback is what's glitchy here. It's not the actual AR part of it. But notice that in this case, even the black parts of this virtual character are opaque. And the reason is because that the real world in this scene is also being rendered in some sort of video display, meaning this is not sort of a see-through rendering device. This is a screen or a display that shows both the real world and the virtual world composited on top of each other. This is not what HoloLens does. If you were going to take something like an Oculus or a Vive or Gear VR and add a pass-through video feed and then composite on top of that, this is the style of technology that you would see. This is the only way that you can render something like black in an augmented reality scenario such that the black would seem opaque. You could imagine, this technology as far as I know does not exist, but you could imagine an additive rendering scheme where you have another channel that just blocks out light. You could call that per pixel dimming. There is no such thing right now, but you could imagine someday that there could be something like that. And that would basically cover both of these kinds of styles of rendering and, in this sort of grand unification. Another aspect of augmented reality, which, this will seem obvious because, if you think about it, there's no other way it could happen. But the perspective of the rendering is always first person. You have no choice but to see things from the perspective that you're seeing. And that's particularly obvious when I'm talking about an additive rendering display where the default is you see the real world from the normal perspective that you have, which is what we just call first person. So the fact that it's a first-person perspective is the least surprising thing you'll hear all day. Actually, there are a few other things I'll say that might even be less surprising. But a key element of this is that so is the manipulation scheme, or so is the user interface scheme, which is not unique. There are first-person shooters. There are definitely other user interfaces that are 3D and first-person. But those are a creative or a stylistic choice. And in this case, it's not a choice. It is just a fact. It's just something that you have to cope with. One of the interesting things about the era that we live in, and by that I mean essentially 2016, this is sort of the year of the headset, meaning this is now when you can actually go to Best Buy and purchase headsets. I don't think that there was a time before now that that was really possible. But what we're starting to see is the beginnings of, I don't know if I'd call it a revolution, that sounds too fancy, but an era of creativity around user interface design that did not previously, it wasn't explored as rapidly as it is now. And so one of the things that people are, like I went to GDC this year, and it was the first year that there was a VR session or a VR aspect to GDC that was explicit. And I was hoping to see a lot of exploration in this area. What I found was a little bit of exploration. I think that next year's GDC there will be a lot more. But one of the examples where I saw something innovative was in order to exit the world that you were in, which is an immersive world, you had to eat a burrito, and that burrito was called the exit burrito. I shouldn't touch this, I suppose. There are other examples, like there's a game that's called Fantastic Contraption, and the metaphor that they created was something analogous to having like pockets and quivers, where if you wanted to initiate a new tool or something, you would reach into a pocket or into the quiver in on your back or on your head or something. I like that one. And another one that I've been really fond of is you see sort of like an iconic representation of a virtual world in the form of a snow globe that's about as big as a space helmet. And you either grab the thing or just kind of plunge your head into it. You just kind of plop it on your head. And it's just this kind of literal, entering of a new world. And then when you do that, it makes sense. Like there's this sort of smooth transition because you see the world approaching you, you stick your head in it, and suddenly you're surrounded by this world. And now you're literally, in that world, and you can walk around and so on. So I thought that was a kind of a cool metaphor. I expect to see more. And there was, this sort of era of creativity around 2D interfaces existed like from the 60s up until the present even. A lot of it was, the initial ideas of like the metaphor of a window, the metaphor of a desktop, the metaphor of buttons and so on. Those came almost immediately, like, Xerox PARC had that stuff almost right off the bat. But you'd see some really, what now seems like, it's hard to imagine that there was ever a time when there weren't tabs. But tabs were a relatively recent invention. Like they were not around in the 70s. I don't think they were even around in the 80s. I think that tabs came up in the 90s. But now that you see them, they're absolutely everywhere, and you can hardly see an interface, a 2D interface that doesn't have tabs. I expect to see something like that with 3D, where people try crazy stuff. Some things will work because it's the best there is for the time, and then eventually it'll get replaced by something else and so on. So I think this will be one of the more exciting parts of this. So here's an example of where somebody tried to create a 3D first-person interface for creating a sculpture. And so, you can see what's going on. There's this like ball that squirts goo out of it, and the goo stays in place. And, it sort of kind of works, except that, if you imagine what this person is doing to create this heart, they've probably got like some sort of a button that they're using to squirt goo, and they're literally drawing the heart by doing this kind of thing, right? Which is really awkward to both look at and to actually do. So, looking at the video, it kind of makes sense, but if you actually saw the person who was doing this, it would be crazy looking, right? So that's kind of weird. The metaphor that I like to, or so the meta metaphor that I like to make for this is it's like we're creating spells. We're not just casting them, though. We're coming up with the incantations and the gestures and all the whatnot that you would do to actually make the spell happen. So imagine, instead of thinking of this like technology, think of this as like a fantasy where you actually are asked, okay, let's say that you wanted to do this or that. What would you like to do to invoke that thing to happen? Would you like to wave your hands around? Would you like to say something? Would you like to just sit there and concentrate? The last part, by the way, is not that far-fetched because there are brain-computer interfaces in the works, and some of them actually do things. I think that, I think there will be some combination of those things that actually happens. So there's another aspect of augmented reality that I'd like to talk about, and I'm going to skip this and come back to it. And that is telepresence. And here again we have the kind of stereotypical Hollywood depiction of telepresence, which is that there's a bunch of people in a room like this, and maybe one of us is a hologram being projected from somewhere else. And conversely, that person probably sees a holographic representation of the rest of us. And again, they're this diaphanous thing. So this is something that Shram Azadi, up until recently a member of Microsoft research, he actually created a system that allowed us to do this. It captured both models and textures in real time, streamed them across the internet and then onto a HoloLens, and then you could render it. So this is totally possible. I think everyone would probably agree that this is desirable. If we could just plop a few sensors here and there and have this work, I'd probably spend money on it today if I could have this today. So this is all perfectly feasible and, I think inevitable. But one of the interesting things is you can't do it today with just a HoloLens. Well, and never could you, because the nature of a HoloLens is that it's a device that sees things from the perspective of the viewer, which is in contrast to the thing I just showed you, where you've got sensors looking at you. So if you want to project your own avatar that looks something like you and that knows your body pose and so on, you can't do that with just today's HoloLens, because it doesn't know anything other than the pose of your head. So you could have an avatar of your head, and that's all, which we actually do, for some things. But one of the things that HoloLens can do, and I've never seen a depiction of this prior to HoloLens, or like no fiction that I've seen has ever done this, is take advantage of that inside-out perspective. So here's an example that does this, and this is a version of Skype that comes with the device and so on. So here's a woman who's wearing HoloLens, and she's messing around with some plumbing, and she's in a Skype session with her dad. Her dad, meanwhile, is using just a regular flat, tablet, aka desktop Skype. And he sees what she sees, and then he's making some annotations here on that scene, but instead of it being 2D, it's actually 3D. And Snapchat has a thing like this where you can mark up the world, and the markup moves with the scene. So that's what's happening here. Her perception of that markup is that it is 3D and world locked. And so if she were to come around from different angles and whatnot, she would see that markup in 3D. And so he's essentially telling her, here's how you do this, here's the direction that you swivel this, nut, and so on. So this inside-out perspective, I still think of as a form of telepresence, and it's a new one. And it's something that HoloLens can do right now, and it's pretty neat. Just to recap, I talked about additive rendering in contrast to composite rendering, and that's what HoloLens is doing now. And this notion of first-person control not just being a choice, but being something you have to cope with. You have to figure out ways of dealing with that. And this notion that when there's telepresence, you have sort of two flavors of it. An inward perspective, which is the one that we're probably more familiar with from fiction, and then this other one that's new and has some interesting applications. So now I want to talk about what has changed in, human and computer interaction, and kind of set up a framework for trying to think about this. So this is the state of the art prior to 2016, which is that we have humans and computers, and there's this overlap region in between them, which we call human-computer interaction. And this is a well-studied field, fairly mature. It's been, people have their PhDs in it, and it's been around for decades. It's not new. It's still an active area, but it's not a new area. And to this diagram, I'll add the environment. And by adding that one region, it creates 3 new overlap regions. And I want to talk about those. So one of them isn't new. It's just conventional reality, the interaction between humans and the environment. That's been going on for millions of years. So there's this other region, though, which is the overlap between computers and the environment. And in a sense, we're seeing a new era of that, meaning HoloLens has all these sensors on it that sense the environment. That's their sole purpose. They're not there like there are cameras on. The majority of the cameras on the HoloLens are not meant for human consumption. They're meant for computer consumption only. And there are other sensors on there that have that same property, meaning that they're not meant for a human to see that data.
How many cameras are there?
On HoloLens, the one that's out now has 6. Yeah. I would expect that number to grow. So I'll be talking more about the region environment understanding. In fact, the group that Matt and I are in is called the Environment Understanding Group. And I'll just say that the overlap region of all 3 of these is, I'll just say that that's AR, that's augmented reality. So another way of looking at this is, sort of from a graph perspective. And again, it's essentially the same thing I just showed you, but I want to show you yet another take of it, which is that we have these nodes in this graph, virtual environment and virtual characters. If you combine those together, you could just say that's the computer, right? And these are elements in the computer. And then real characters, that's humans, that's us, right? So now I want to add one more node to this, which is the real environment. And again, you'll notice that by adding a single node to this, the number of combinations grows by more than just one. We've got 3 additional edges in this graph. And again, one of these edges is not new. It's just the interaction between the real environment and real characters and conventional reality. This is a million-year-old thing. But we've got these 2 new edges that are interesting to look at. The connection between the real environment and virtual characters, and the connection between the real environment and virtual environment, and that's what I'll talk about for the next several minutes. What those modes of interaction are and how we enable them. And furthermore, what, I think the reason why they would be interesting will be evident. So this is probably the second least interesting thing you'll see all day, which is a guy grabbing a teapot. But there are some subtle things going on here that require an immense amount of sophistication. So for one, this guy's thumb is occluding the teapot handle, and at the same time, another part of the teapot handle is occluding his finger. I showed you earlier a picture of Cartman who was occluding the scene behind him. This is the first time in this slide deck you've seen a case where the real world, actually it might not be the first time, because maybe the second Iron Man thing showed it, but actually no, I think he was always occluded by the hologram. So this is probably the first time you've seen in this deck a person, or a real world thing occluding a hologram. This is actually amazing and takes, a huge amount of processing, a special kind of sensor, and a whole team dedicated to doing just this. So I'll explain how that works later, but I just want to show another video of this. So here's a guy who, I don't know what's going on. Video's not playing. Okay, so the guy's occluding the hologram. He's going to walk behind there. The hologram's now occluding him. He'll come around the front. He'll occlude the hologram again. Now he's going to go behind there, and we'll see him hug the thing. And so both of those things will happen simultaneously. The hologram's occluding him, and he's occluding the hologram simultaneously. So this happens to be a composite view, but the technology behind, while the rendering technology is different, the technology for how you would enable this is the same, whether it's composite or additive display, and I'll come back to it. But the point is that this is a 2-way interaction that is visual. And I want to show another interaction that is, I'll call it physical, and that is having virtual objects that are moving interact with real objects that are static. And by interacting, I mean physically, not just visually. So I'm going to pause this because the Jitter is making me crazy. What's going on here? Okay, in the upper left corner is a live stream of a color camera, and the upper right is a normal map rendering of the scene, meaning of the surfaces. Lower left is color composited with real and virtual objects, so this is essentially the AR display that a person would be seeing. And this is just another rendering of this kind of scene, except that it will include both the real and the virtual. Okay, so watch what happens. So watch what happens is on the lower left you'll see a bunch of virtual yellow balls being thrown at the scene, and they just kind of bounce off of the scene and come to rest on the surfaces of the real scene. So this is what I'll call a one-way physical interaction where virtual things care about the position of real things, but real things don't seem to be having an active influence on the virtual things, meaning that the virtual things are just kind of responding to the static scene. What about the other direction? Can you have something that's real and moving manipulate something that's virtual? So both of these things are sort of interacting with each other in a quasi two-directional way. So in this scene, the balls are virtual and the hands are real. And so here you can see that the hands are scooping up and playing with these virtual, toy things. And yes, so the answer is yes, we can do that. Great. So these are the modes of interaction that I want to be, clear about. That when I'm talking about augmented reality, I mean both a visual and a sort of quasi-physical interaction. And I mean that in two directions. And the technology between one direction is not the same as the technology behind the other direction. And so the rest of the talk, I'll be talking about those technologies. I want to take one more tangent, though, which is that I want to talk about the nature of reality. And so I forgot to mention this, but one of my pieces of background history is I have a degree in philosophy, so brace yourselves. No, seriously, this is a kind of semantic thing where this term reality has a double meaning, and most people aren't, well, I don't know that people are cognizant that they are actually conflating two unrelated terms to mean the same thing. So if I said augmented reality and virtual reality, and almost in every talk or session or whatever that I've been to, people say augmented and virtual reality almost like there's only a one letter difference. Like we can say AR and VR, if you could make a little glyph that was A and V simultaneously, it's almost the same thing, right? Well, actually it's quite different. So the difference isn't just in the augmented versus virtual part. It's not just that you have, in one case, augmented, in the other case, virtual. It's that the word reality in these two actually is talking about a completely different and unrelated reality. In the case of virtual reality, the reality that we're used to is completely replaced by a different reality. So in other words, this reality is replaced completely by one that is entirely fabricated. And that can be both a benefit and a drawback. Meaning, if you want to create a virtual reality experience, you have no choice but to create everything in that world from scratch. There is no reusing of assets from the real world. On the other hand, that gives you the freedom to do things that are physically impossible, or even possibly, sort of mathematically impossible, like Escher-type connectivity or topologies that you probably couldn't express, in the real world. In contrast to this is augmented reality, where we start with the conventional reality and we add something to that. And so this again can be both a benefit and a drawback, meaning the benefit is I can just take this room and add one little element to it, and bingo, I have augmented reality. Might or might not be useful, but I have achieved my goal, right, which is to have augmented reality. The drawback is if you want to have a scene or if you want to have an experience where I can do some sort of ballroom dancing in here, well, I guess you couldn't do it in virtual reality either because the tables are in the way no matter what. But the point is that with augmented reality, that was I should come up with a different example. The point is that in augmented reality, you both have the benefit of using the existing assets, which is the real world, but you're also constrained by that. You have no choice but to see this table and see all the people in here and whatnot. It's a very practical and very important difference, and it's going to open up, and it has opened up, a whole new aspect of environment understanding, which is semantic understanding. Meaning that if I want to create a play space in this room or in any given room, I have to actually understand what the things are, not just where they are and so on. An example of this is in HoloLens, there is a game that's called Fragments, and it's this kind of murder mystery game. And one of the things that happens in there is there are virtual characters that interact with you, and they will have conversations with you and have meetings with you and so on. And they will do things like sit in the chair that's right there. They will sit in the chair and face you and do these things that feel kind of natural. There are other examples where people will create games and they use the existing terrain to lay out the level. So the point is that that notion of having to use the existing space is neither easy nor it's kind of it's hard to do, but it's kind of cool. Like when it happens and it comes together and you see like a virtual character sitting in a chair, suddenly they feel much more believable and realistic and like they belong to the scene. Okay, so that was my little philosophical tangent. Now I'm going to talk about tracking technology, and I don't know if there will be time. I suspect there won't, but there's another piece of technology that I would like people to understand, which is surface reconstruction, which is the part that tells HoloLens where surfaces are. But if I only have time for one thing, I'll talk about tracking. So how do we make holograms that seem to be world-locked? The answer is entirely based on how we track the position of the rig. And the rig includes cameras that are used to just do the tracking and also the display. And so we need to know the relative location of the cameras that do tracking and the display. But the point is that that notion of world locking comes entirely from knowing the trajectory of this rig. That's all there is to it. It doesn't actually need to know, well, I'm trying to, it's hard for me to say what else it would have needed because it doesn't need those things. But the point is that if you thought that there was anything more to world locking other than pose tracking, let's talk about that because there isn't. It's something that I want people to understand.
There's a little.
If you have one eye, it still works. So I'm going to spend most of my explanation of this on a single diagram, because this diagram has essentially everything you need to know in a nutshell when it comes to tracking and both the benefits and the drawbacks of how this works. So this diagram is going to be a graph in the computer science sense of a graph, meaning that it'll have nodes and edges. So I want to explain what the nodes and the edges are, and then you'll understand tracking. A node has two meanings. One of the meanings is that it is a picture of the world, and that picture is necessarily from a particular point and looking in a certain direction and with a certain orientation of that frame, which means that that picture of the world sort of automatically corresponds to a coordinate frame, namely the one where one of the axes is pointing in the direction of the view, one of the axes is going to the right, and one of the axes is going up. Okay? So that's already a lot to digest because, but I'll come back to why. But a key here is that this is one of the coordinate frames. This is a coordinate frame. Okay. Now, if I take a second picture, there's another node that shows up in the graph, and again, that picture will have its own coordinate frame. And if these two pictures have something in common, that is something visual in common, then it will be possible to determine the relationship between these two. And again, there's going to be two levels of meaning. One of the aspects of that relationship is what I'll call correspondences, meaning something visual that is in common. And the second part is the transform between coordinate frames. So if there was a coordinate frame like this, I don't know how to depict it. I don't know, something like this. I need a third arm. And there's another picture like this, then there's going to be a coordinate transform between them, whether we know it or not. And if we do know it, then I'll draw a link here. Okay? So now I'm going to take a third picture and something magical happens, which is that, let's say that in this case, all three of these have something visual in common. So now I have three pictures, I have three coordinate frames, and if they all have something visual in common, then I can compute what the transform is between these three. So let's pretend like we're in an imperfect world, and the measurements that I take are not perfect in some way, and that the algorithms that I run are not perfect. They have finite precision, for example. Let's say that the image sensors have noise in them. Let's say that there's some distortion in the lens that I can't trust will be constant over time, like maybe thermal deformations change it and whatnot. That means that when I do the math, the numerics, to find out what these transforms are, they aren't perfect. So if I start at one point in the graph and I go around and come back and I concatenate those three transforms, I should get the identity matrix. But I won't. It won't be exactly the identity matrix. Phrased differently, if I want to get to this node from this node, I have multiple possible paths. I could either do this, where I take these two hops, or I can go directly and take that one hop. Either way, it's going to be wrong by some small amount. But even more interesting is the fact that they're wrong in a way that is different from each other. So what I'm going to do is continue drawing this graph, but in a very particular way, which is that imagine that this is an art gallery, and then I came in through that door, and I'm going to be looking at all the art on the walls of this gallery. So at no point in this scenario will I stand somewhere and then look across the room and see the rest of the room. I'll always instead be kind of, strafing along so that I only have this sort of limited view. And furthermore, let's say that when I first entered the room, I saw a piece of art that I wanted to remember. Maybe I want to buy a copy of it or something. So I'll put a hologram that's like a bookmark or something. And when I place that hologram, I'm going to place it relative to this coordinate system. Okay? So as I walk around the room, sometimes these pictures will have enough overlap to create a link between its neighbors, but not all the way across. So in other words, when I get 3/4 of the way around this room, I don't have a direct link to that first one. Because remember, I'm looking at the wall. So in this scenario, if I came in through that door, I kept coming over here, I don't have a direct link from here to the door. So let's say that I turn around, and before the algorithms run to figure out what that link is, there's a certain amount of time that passes when I want to see the hologram that I put on that piece of art, but from my current coordinate frame. In order to do that, I have to have concatenated some combination of transforms, okay? And so I could just pick some path through the graph, let's say this one. So I go through these 3 hops. And you can imagine that if I had the patience to draw a more convoluted map in PowerPoint, and that this were not just one room, but something like the Metropolitan Museum of Art, which is extremely labyrinthine, and you can get lost in that place. But you could imagine that just before I come back and sort of close the loop, the amount of error that accumulates in here can be arbitrarily large. And I mean that truly arbitrarily, because I can always construct a path that is as long as I like. Right? So that means that hologram that I placed over there, before I make a direct connection, well, it could be off by an arbitrary amount, both in terms of rotation and translation. But as soon as I stare at it long enough and I start to see a correspondence between this picture and that picture, then I can form a direct link. And now the most reasonable path through this graph from here is not to go all the way around, but to go this way. And it's probable that this path will have less error, but the fact that it will have different error is even more interesting, in that what I'll see is the hologram will jump from whatever amount of arbitrary amount of error from this circuitous path to the different amount of error, probably much smaller. And so you'll see a hologram go from wherever it is to back to probably where it belongs. Another interesting part of this, though, is that let's say that I'm standing here. No, actually better. Let's say I'm standing right here, sort of in the middle of these 2 nodes. And I'm looking at a hologram that's anchored on this one. Okay? If I stand here, it seems reasonable I would take one of these paths. If I'm standing here, it seems reasonable I would take like this path. If I'm somewhere in between, it's not really clear which path I should take. And you can imagine sort of teeter-tottering across some point where the best path will alternate depending on where I'm standing. And you can always construct a scenario where you find exactly where that dividing line is and just kind of teeter-totter across it. So what you could see then is a hologram sort of bouncing between 2 states. It's this kind of bistable state. So there's a lot of information to soak in there. But one of them is that there is no such thing as a world coordinate frame. If you're used to developing 3D content, like for video games, you're probably used to thinking, oh, there's a world coordinate system and then there's the camera's coordinate system. And the transform between them is known by construction. There's no error in it and there's no ambiguity. None of that is true here. Not only is there not one true coordinate system, but the relationship between coordinate systems is not perfect. Furthermore, here's yet another thing. As we build this map, we can run algorithms asynchronously that correct some of these errors. So not only is this not sort of perfect, but it's also not rigid. So you can imagine these things are in some sense squishy springs, or they're springy. So this notion of like where is a hologram can change over time. It can change based on where you're standing, and so on. Furthermore, you could also imagine that you could create a link here that it shouldn't actually happen. Like let's say that I have a picture of the Mona Lisa here, and then also another one that's somewhere else, and I look at the Mona Lisa and I'm like, oh, that's cool, power off the device, walk over there, face the Mona Lisa, power it on again. it's possible it'll say, oh yeah, I recognize this place. It's the place that has the Mona Lisa in front of it. So it'll create possibly a link in the graph that shouldn't exist. We call those wormholes. All of these things can and do happen on a regular basis. I believe we wanted to keep 15 minutes for questions. So, and this is kind of a natural stopping point because the rest of this is either about a new technology or additional technology or about sort of refinements of how this happens. But, oh, there's one other take-home I wanted to mention before we go into questions, which is the way that I constructed this particular scenario is to have as little line of sight as possible and therefore the maximum amount of error possible. So what I'm really basically showing you is the worst scenario possible for map integrity. So if you were going to create a scenario for users to consume, you would actually want them to map the space both thoroughly and completely before you start placing holograms. And by thoroughly, I mean don't have them face the walls. Have them do the opposite of that. I mean, you don't literally want them to do this because that's crazy, but you don't want them to do this because this is even crazier. So don't do either of those things, but err on the side of having them look, sort of taking in the scenery. So that's what I mean by thoroughly, and what I mean by completely is have them do kind of a circuit of the space before you place any holograms. That would be ideal from the programmer side. There's also what's ideal from the user side is that everything just works. We have to find a compromise in the meanwhile before we, until we solve this in a better way. Okay, so that's a lot of material already. And the part that I'm not getting to is about surface reconstruction, which is how do we actually measure where surfaces are and then create a model from it. But the short story is we have a device, I mean, you're familiar with it, I'm sure, which is Kinect is an example of this, which is a depth camera, which can tell where surfaces are. And then there are some fairly straightforward algorithms for how to aggregate that into a single sort of unified representation of space. And you can deliver that in the form of a polygon mesh, which is what we do. And that's what most game developers are used to doing, and most game engines are used to consuming. That is the technology that allows real things to occlude virtual things. All you have to do is render that mesh in an invisible way, and it'll just occlude the virtual stuff. And similarly, once you know where those surfaces are, you can bounce virtual things off of it. So the way that I like to think of it is, there is no such thing as mixed reality. There's only virtual reality. It's just that some of that content was sourced from the real world. So that's just my way of thinking of it. So all right, so that's where I'll stop sort of dishing out info, and now I can take questions.
If there are questions online, I will have them IM to me.
Okay.
So if anybody in our online audience wants to ask a question, please type it in the IM box, and I'll read it out. Otherwise, feel free to take questions in the room.
You had a question.
So in this scenario, like this algorithm runs on purely visual nodes, right? Like you see your access based on what you see. Well, how does things that are radio based or maybe Wi-Fi signals or Bluetooth beacons fit in this scenario?
So you're sort of headed in the general direction of something that I didn't get to, which is I just described visual tracking. There are other modes of tracking. Yet another is inertial, where you have we call it an inertial measurement unit, which is a combination of an accelerometer and a gyroscope. So it tells you acceleration and angular velocity. And if you had a perfect IMU, you wouldn't need visual tracking. You could just use the IMU. But the reality is that all these modes of tracking have various trade-offs. Like some have benefits. One of the benefits of inertial tracking is it is extremely simple and extremely fast. But it also has a drifting problem. And you can combine this with visual tracking and get the best of both. It actually gives you better accuracy than either alone. And also you get the benefits, like you get the low latency benefits of this with the no drift benefits of visual tracking. So the beacon-based stuff that you're talking about is yet another mode. And so you can imagine just adding it to the mix. And like an example of this is Vive, which uses they call it a lighthouse. It's kind of a beacon-ish. It's unique as far as I know. There's no other tracking system that's quite like it. But it uses that plus inertial, I bet. I don't know that they use inertial, but they almost have to. And then Oculus, which has an outside-in vision-based tracking system, which is similar in spirit to what motion capture systems use. Then you can also imagine these sort of LORAN type, beacon-based, triangulation-based, like GPS is an example of that. And that's actually what happens on your phone. It has GPS, but GPS is very slow and not very accurate. And so if you go into a tunnel, you could be sort of lost, but it has an inertial measurement unit in here, and so it'll do inertial tracking there. So the point is, I guess, you can combine the two. I'm not sure if that answers your question, but you could also imagine, though, that those other systems can do what we call coarse relocalization, meaning that you can know essentially sort of, let's say that, you've been to the other studios in Microsoft, like studios A, B, C, and D, all pretty much have that same kind of swastika layout, with the 4 prongs. And you could imagine that being in any particular conference room or even the kitchenettes in there, it looks visually very similar to others on campus and others even in the same building. So how do you discriminate? And one possible answer is you could use Wi-Fi as a coarse reloc to know essentially what building you're in, maybe even what floor you're in. And there's also 2 kitchenettes, so you can imagine even discriminating between those. So that's another use case. Also, most Wi-Fi radios, maybe all of them, have FM radios in them. So you could imagine using FM triangulation as a modality for that. GSM would be another one that's already in use. These things, even when there's no GPS signal, my understanding is that they'll also use GSM triangulation and so on. So all these can work together, and the more data you have, the better, essentially. Yeah.
Earlier you mentioned when we saw the person drawing the heart with the arrow through it, that they were probably moving their head. How is HoloLens made it better?
So HoloLens can also track where your hands are, and so you can do things like, sort of manipulate a cursor or a brush or a tool or something like that with your hands in 3D like this. You could also imagine if we, HoloLens also comes with a thing we call the clicker, which has an IMU in it. And so you can use that for manipulation as well. You can imagine other controllers that could play well with it. Like HoloLens runs Windows 10. If you have a Bluetooth device that is some sort of controller, it will just work with HoloLens. So in that sense, it is, sort of all-inclusive of any sort of controller technology that comes up will just play well with that. But in addition to that, there is that hand tracking aspect to it. There's also, well, yeah, I'll leave it at that. Yeah. Other questions? I know somebody else, Ben.
So, sounds like a ton of math to be running.
Quite a bit.
Quite a bit. And presumably a large amount of memory, especially if you're walking through the Met, like you're trying to remember, well, I've gone this crazy labyrinthian path, and now I turn around and I have to know which path did I take, how many of those nodes did I hit, which of those are viewable now, assuming you've got a complete enough graph.
That's right.
Are there techniques that we use to make that faster or simpler or just not require a giant mainframe somewhere?
The answer is a combination of tried and true stuff like divide and conquer, paging stuff. There's working sets and there's backing stores and there's caches and so on. So part of the answer is that sort of way of dividing up a problem. Another part of the answer is this thing that people have come to know as the holographic processing unit, which is the third major processor on the device. I often get asked a lot of questions about it, and I generally feel like if it's on Wikipedia, I'm okay to talk about it. And to my surprise, that's probably the best kept secret of any aspect of HoloLens, and so the part that I regrettably probably keep the most shut up about. But other than to say, which it is just a third processor that we use to do a lot of this math. Maybe in a scenario where I wasn't being recorded and publicly, who knows who's listening, I might say more, depending on who was in the room and what was tented. But But I guess I could just leave it at that. It's just another processor that that's how we distribute the compute load. As far as the memory and so on, I mean, that's where it just comes down to you have to be smart about spatial partitioning algorithms, but that's not an area where you necessarily have to innovate because it has a very long history, spatial partitioning algorithms. But at the same time, it's fairly far from a completely solved problem. And in fact, we have at least 2 organizations on campus that I know of that are specifically focused on that specific problem, which is how do you partition space. I mean, to put it in a nutshell, that's essentially what they're doing. And also, how do you get that to be such that you can share that with other people, which is another important aspect, right? So it's what we've done so far is reuse known stuff, and we found it to be inadequate in certain ways, and so it's an active area of research. Yeah.
There's a remote question, which is in terms of augmented reality UX, a lot of what we've seen so far is either flat surfaces imitating desktop or mobile UX, or apparently flashy but impractical demo stuff. What's the state of the art right now?
So the thing about the flat stuff is it's really like legacy and you have to support it. It's not, like if you put on a HoloLens and go to the store, you'll see most or all of we call them flat apps. So in other words, if there's an app in the Windows Store that's a universal app, it just runs on HoloLens. That's the kind of you have to do that stuff. It's not because we think it's the best way to use a HoloLens, but you have to support it. It is cool though that in my office, I've got remote desktop, settings, Outlook calendar, Outlook mail, I don't know what else. There's apps all over, so it's essentially like I have several dozen monitors in my room. So even in the flat app scenario, HoloLens gives you essentially an infinite monitor. And because it supports Bluetooth mouse and keyboard, that means that I have the sort of data entry methods that I'm familiar with and that are high speed and so on, in addition to using gestures and voice. What I think is the state of the art is, I sort of touched on at the beginning, you have the exit burrito. I think this is the area that is the most exciting in that it has so much undiscovered territory. So the state of the art really is like Wild West frontier. I don't know which of those paradigms or which of those metaphors will stick. And in the meanwhile, it'll almost be sad when we find what works, because we'll have left behind all the crazy stuff that will have been fun to try, but it won't be very practical. It'll be before, I remember in the late 80s, some people had thumb trackballs, some people had mice, and there were other input devices. And you would just as often see a thumb trackball as a mouse, because some people just thought that was better. And now, you're the weirdo if you've got anything other than a mouse and keyboard. Some people have crazy looking keyboards and so on, but they're still kind of the weirdos in a good way. I've got a crazy keyboard, but or in some of my machines. But the point is that that was a fun era to have lived through, and I think we're entering that era now. So the state of the art is a bunch of crazy stuff. Part of what goes with that, though, is on all 3 of the headset things that are out right now, HoloLens, Vive, and Oculus. You could say Gear VR is another one. They all have completely different, totally disjoint controller schemes. By disjoint, I mean none of them play with any of the others. Vive has a very interesting 6-DoF controller, and it's very precise, but extremely bulky. It's way bigger than a remote control. It's more like, it would be like wielding that power strip without a cable. It's like these weird baton things that I don't know that, it has.
The ring at the top.
No, there's a different, I might be conflating, but yeah, the touch controller that's coming out actually goes around your hand, and it has some other interesting things. So I think the metaphors will be subject to the controller, the whole, whether there was a question in the 80s and 70s as to whether or not mouse and keyboard was viable, because a lot of people assumed that no one would ever develop the hand-eye coordination to be able to use a mouse. And there was a time when that seemed evident, because you would just pick up a mouse for the first time and you'd be like, see, look, the cursor is going, I have no control, it's hard to click the button. but people just grew accustomed to it, and now like 5-year-olds can do this. It's not a problem. So we'll see what the controller schemes are that kind of come out. Yeah.
Is there any way to have a augmented reality where multiple people share the same display? For example, a car where something's being projected onto the windshield and both the driver and the front seat passenger can both share the same view, and the passenger doesn't just have some really weird parallax for both the drivers.
So I'll divide that up into 2 parts. One of them is the sharing part, and the other one is operation in vehicles. The sharing part already exists today. HoloLens already has a way of sharing holograms across devices. That was out as of day 1, released to manufacturing, had that feature. I would expect to see that to become easier to do than it is right now, but it's really just sort of syntactic sugar over an existing functionality. It may be more than just syntactic sugar. There might be other ways of making it faster or better, but it's already there. Operation in vehicles is a different problem, and it has more to do with tracking and less to do with the sharing. It works, but it isn't supported. I, for example, flew in a zero-gravity flight because we had to test this thing before we sent it to the space station, which is a vehicle after all. And so I can say firsthand that it does work even when you're not working. But it doesn't work very well in vehicles at the moment because it's not a scenario that we've gone after. And essentially the reason is because of that conflict between inertial and visual tracking. You have to be deliberate about how to resolve that conflict.
Can I actually clarify my first question?
Sure.
I think you may have interpreted it as the 2 people are each individually wearing their own headset.
Yeah.
And what I'm thinking is being projected onto a display where the people don't have to be wearing headsets, but they're both just like the key and actually.
Yeah, I don't know much about other display technologies other than going to various tech shows and so on, and none of the ones that I've seen seem particularly viable. Like the one that would probably work the best for sharing without parallax is like there are these things that we call them blenders, but they're just basically some kind of a spinning display that you stare at from the outside looking in. It wouldn't be particularly suitable to a car. And if you had a heads-up display we call it Pepper's Ghost, where you display up from like a projector that's bouncing off of a semi-transparent display, that has to be calibrated to a person. And it's not even just sharing, even like the one person, their position has to be tracked.
I see.
And people do that. There are actual displays that have that property that they know where your head is, and so they give you that illusion of world-locking holograms. But it only works for a single person. Then there's yet another, which is you go up on stage, there's a big hologram being projected. There's actually, you could pay for the privilege of seeing this in concert, actually in April here in Seattle. It's a Japanese anime character who goes on tour. She's utterly synthetic, both visually and her voice is totally synthesized. And you can go to concerts and see this. I think there was a Michael Jackson one like that as well. So that's shared, but it's not particularly convincing as a 3D thing, except that you're super far away from it. And so even though it's flat, it seems 3D enough, sort of like you seem 3D enough to me because I'm back here. And if you were even farther away, the difference between you and a cardboard cutout wouldn't be that important, So that's essentially the state of the art for that. Yeah.
At least visually, right?
Visually.
Well, I think we're out of time, so
Yeah.
Thank you, Michael, so much for coming to speak with us. This was
Sure.
really, really awesome. Thanks again.
Yeah, sure. Thank you.